Now, the next case is the uniform plane waves in lossless dielectric. So, we'll consider the uniform plane waves in the dielectric, which is lossless in nature. And how you define the lossless dielectric, or it also be called perfect dielectric. The lossless dielectric are those dielectric where we have no free charges, that is rho v equals to 0. And second condition, there is no conduction current, that is the conductivity of this media is 0. So these are the two conditions. Rho v is 0 and sigma equals to 0, that is there is no conductivity, no current can flow in that medium. So that media is called the lossless dielectric, or also called the perfect dielectric if these are exactly zero, these two terms. So in that case, again, divergence of D will be 0 as rho v is 0. Divergence of B is always 0. And curl of A is minus del U over del T. And curl of H is only remains to be displacement current density. And the condition current density will be 0. So these are the Maxwell's equations for lossless dielectric. Now here we will consider the time harmonic field or the sinusoidal time varying field, and for this type of time varying field we will obtain the wave equation and their solutions. So in general, in nature, the almost many of the phenomena is governed by the sinusoidal variation. That is, the scientists have seen that many phenomena is varying in the same pattern, and they find that these patterns are almost same. So they term they discovered the sinusoidal function, which is the same pattern, same variation as exhibited by the nature. So in nature, the variations of many phenomena are governed by the sinusoidal pattern. So we will now focus onward to the sinusoidal time varying fields. So for the sinusoidal time varying fields, uh, for example, if the fields are not exactly sinusoidal but they are periodic, so we can decompose any periodic function or any periodic signal in terms of their sinusoid harmonics. So if we understand the sinusoid time varying fields, then we can understand any periodic signals. So using the Fourier series or Fourier transform, you can decompose any periodic fields in terms of their sinusoidal fields. So understanding the sinusoidal time variation field will ease to understand the any periodic nature of the fields. So let's focus on this sinusoidal time varying fields. So for this time harmonic fields, we have the phasor forms. That is, any time varying fields can be represented in terms of their phasor forms. So you have uh, fields which is time varying, which is time harmonic. You can represent in terms of their phasor form like this. The real part of Es e to the power j omega t. This is the time part, and this is called the phasor form of this field. And this phasor form is independent of time. This is a function of spatial coordinate only, that is x, y, and z. And we have split the time part, and this is the time part. So the phasor form will be a function only for the spatial coordinate. So the Maxwell equations for phasor forms we have already uh, seen in the previous lecture is here reproduced here. The divergence of ds equals to 0. Now it is a ds, and divergence of b, it is also a bs equals to 0, and curl of es is minus j omega bs. Now previously it was in general del b over del t. Now due to the phasor form it will reduce to the minus j omega bs. So there is no time component here in this equation. Similarly, curl of h will become curl of hs equals to j omega ds. So now these equations are independent to the time. Now to find out the wave equation, just using the same procedure, that you pick up this equation and take the curl of this equation both side, and then find the wave equation. So again, going through the same process, you will obtain the wave equation. So this is a wave equations, del square es minus omega square mu epsilon es. So now here is no del ey del t, del square e over del t square. Only you have the es form, phasor forms. So you have omitted the derivative of the es with respect to time. So instead we have now the omega square minus omega square. So this similarly you can obtain the wave equation for the magnetic field also. So we have now two wave equations in phasor form. Del square Es equals to minus omega square mu epsilon Es, and del square Hs minus omega square mu epsilon Hs. And these two wave equations in the phasor form are called the Helmholtz wave equation. They have the special name, so these are the important name, and we will also see these equations in the later classes and other courses. So these equations, the wave equations in the phasor form, are called the Helmholtz wave equation. Now solution of this wave equation will give you the electric and magnetic fields. Okay. And we are focusing on the uniform plane wave. So uniform plane, already we have defined that they are independent to the two directions, and it is only varying in the one direction. So here let's suppose the wave is propagating in the x direction, that is wave is varying in the x direction, and the variation in with respect to y and z are zero. Second, we have already seen that when the wave is varying in the x direction, propagating in the seems to propagate in the x direction, the x component and hx component will become 0 and the wave will purely transverse. So we can write this as, now when we open this one, so the application of this, so again you will have the del es over del x square, and it will be square. So as similarly we have a plus del square es over del y square, but these two term, the variation of in term of y and z is 0, so those two term will become 0 and you will have this equation. Now here you have this equation, this, so we can represent this constant minus omega square mu epsilon to be minus beta square, some constant. We will see in later sections that this beta is called the phase constant. So let's assume here it is some constant beta which is equals to this value omega square mu epsilon. So beta equals to omega under root mu epsilon, and it is function now. Now solution of this wave equation uh, will become look like, okay. And next thing is here, now simplicity, because we have seen that this is in es is independent to the uh, y and z, or it's only a function of x. Second thing, the x component 0, only we have two component y and z. So to further simplify, we can assume that the z component is 0 and only e is along the y axis. So what it mean by this one, you have x-axis and you have this y-axis and you have z-axis. So what you said, the if the wave is moving in this direction, then the electric field or the magnetic field will be perpendicular to this direction. They will lie in this plane. So maybe here this is the electric field. So for simplicity, we can assume that now z component also 0 and it will lie in the y. If this is a y and this is z and this is x, so we assume that the component ez component is 0, only we have this component. So now this will be instead of this one, what you have, this will be the case simplicity. And how we can use this simplification, because if you have, let this is y and this is z, so if you have any vector which is representative of this one y and z, so we can reorient this coordinate x axis y and z, so that it may be aligned to this axis. So what we can do, we can have y in this direction along this one and z here, and you have the actual field is here. So just you can make reorient or transform this coordinate so that this two-dimensional plane, so that now the y-axis will come along this one, along the electric field, and then so it will become the same case. So for simplicity to understand the concept, we are assuming this case. Or what we can say, that the z component is 0 and we are focusing only the y component. If you understand this phenomena, then you can generalize for any case. So let for simplicity, ES only y component, ES equals to ESY. That is, orient the coordinate system so that the ES direction aligns with the Y direction. So now the equation will become even. Now this is a function of y. This is have the only component y component, and it is a function of x. The two things. Now it will be a function of x, and it is a component direction is the along the y direction. So electric field direction along the y direction, and it is varying with x only. The solution of above equation, if you see that, you can find out solution, but you can just here you can verify the solution of this equation, because here now we have, instead of del square e over del t square, now you have esy. So not any function can be a solution of this. In the previous case, now you have a specific function. So this type of function, that is the complex sinusoid, will be the solution of this in this form. So now you can verify just when you take the double derivative of this function. Let's take this, focus only this part. So when you take a double derivative of this one, so what you will get minus j beta whole square, and it will be c1 e to power minus j beta x, which is already same which we have considered. And here minus j beta square will be minus beta square. So you will get this will be the solution of this one. Similarly, the same case will be here. If you take this one independent part and you verify with this one, this is also a solution of this equation. So these two joined together become the general solution. So one is minus, another is the plus. So these this is the general solution. Uh, this solution, general solution for this equation. Yeah, and ESY equals to ESY. Though this is a magnitude, the direction we have already assumed that ESY is along the y direction. So finally, what we have, this ESY is equal to ESY AY. Now we can say that there is a function of x. This is bx here, and it is the direction is AY. Where C1, C2 is any constant, uh, and they are obtained using some conditions given for media, and how we inject the power in the space, how we generate this signal, or it also depends upon the boundary conditions. So we have obtained the solution of one wave equation with respect to E. So we got the equation of E. Electric field is this, it will be like this. Now we can also obtain the H here. Now because E and H are dependent using the Maxwell's equation. So once you know the E, you can find the H using the Maxwell's equation. So you know E, now you can find the Hs. So using the Maxwell's equation in the phasor form of this kind, where you have a curl of Es equals to minus j omega mu Hs. So using this, you already know Es, you can find the Hs. So Hs vector equals to minus 1 over j omega mu and the curl of ESY. Now, what is this del operator? Del after we have three components, 1 over del x, Ax plus del over del y, Ay plus del over del z, Az. So because this is independent to, this is the component along the y direction, but this is a function of x only. We have this one x. So when you take del over del y, del over del z, they will become 0. So here we have omitted this part, only this will remain term. So these two terms will give you 0 always when this function is a function of x only. So these two terms will be 0. So we are only writing this part, and we can replace ESY with this equation. And because you have this a vector, and this is a unit vector, and these are the magnitude of this one, so you can take it out and you can have the curl of this. So del over del x over c of c1, this function, into curl of this will be ax curl of curl with ay. You will take ax and ay. This will give you the az. So if you have ax, ay, AZ, then curl of AX with AY will give you the this one. So you have this, you have to move in this fashion. So when you take curl of AX AY, it will give AZ. If you take AY curl AZ, A cross product of AY and AZ equals to AX. So we will have, so here will be AZ. So direction of the H is comes out to be AZ. Now operating this one, you can have a del over del x. You can take out here b, and finally you can get b over mu omega mu, and this will be under root epsilon mu. So this is the magnitude of the magnetic field, and the direction of this magnetic field is comes out to az. So direction of E was in the y direction, and direction of H comes out to be z, and these two are perpendicular. So what it means that electric and magnetic fields will be perpendicular to each other. So earlier we said that the electric field is perpendicular to the direction of propagation. If your direction of propagation, so if it's the x direction, so electric field will be perpendicular to this. Now if we choose our direction of E, the z will be, H will be perpendicular to this also. So H will perpendicular to this direction, or H will also be perpendicular to the E direction. So E, and if this is a E, then H will be upward direction. So these two will be lying in the plane perpendicular to X, and these two itself, they themselves be perpendicular to each other. So these two electric and magnetic field will always remain perpendicular to electric to each other.